Good evening, everyone, and welcome to the vacuum transport seminar of this semester. We're very happy to welcome you tonight and kick off the new semester's edition of our vacuum. With this session, we would like to introduce the co-founders and hosts and the partners, and to give you an overview of the seminar. And also, we already have first guests tonight who will talk about the tunneling aspect of Hyperloop. So as you can see here, again, the hosts are Swissloop and Eurotube in a partnership with ETH Zurich. And our partners are the University of Applied Sciences Emden Leer, the University of Oldenburg, the Institute of Hyperloop Technology, the Technical University of Munich, TUM Hyperloop, the Karlsruhe Institute of Technology, and Missouri Hyperloop. So a warm welcome from all of us, and we're very happy to guide you through this semester's edition and learn more about Hyperloop all together and foster our collaboration and all our discussions. To give you short content of our seminar, as I said, now we will quickly give you an introduction and also tell about the goals of the seminar and also the schedule, which is on our common website, and afterwards a short intro into Slido, which is our tool where we collect all the questions and then do the question round. So all of the partners and organizers are now going to give a short introduction about their background, about their association, to give everyone an insight who we are and how this seminar came across. My name is Nathalie Nick. I'm representing Swissloop in this seminar. I'm from ETH Zurich, from the Swissloop team, which is our Hyperloop team at our university. We do research on Hyperloop prototypes since 2016, when the project was kicked off. We participated in multiple SpaceX competitions, and now we're engaged in the European Hyperloop Week, which will now take place for the second time this summer. Like many Hyperloop teams, we're always in close contact with the sponsors, but the whole development is done in-house by the students. We're an active team of 30 students, and we're as well a focus project of the Department of Mechanical and Department of Mechanical Engineering and the Department of Electrical Engineering. To give you a short overview, this is Swissloop's history. So it was founded in 2016. Here you can see an overview of all the teams with the corresponding pods. And as you can see, so that the whole time span of a project always lasts from around September, October until July. So all those people, all those teams worked within Swissloop for roughly a year and developed the prototype and also built it and then competed with it at the end. And at the bottom right, you can see this year's team. So the active team now, who is now eagerly starting to build and test the prototype. Here, in comparison to the previous slide, you can see an overview of our pods, what we're doing research and tests on. So we started off at the very beginning with the cold gas propulsion, then it was followed by a pod with electric motors. And from then on, from 2018 on, we focused a lot on linear induction motors and its propulsion. And yes, so afterwards we had 3 pods developed and produced where this technology was further refined and improved. Exactly, and our next pod will then be revealed in around June.
We're
exactly.
looking forward to that.
Thank you. Thank you. Yes, we're also. Yes, will be nice. So I mean, then in the next semester we can then include the new pod also in the introduction. Now I would already like to hand over to Daniel, who is from the Eurotube Foundation, and to give a short introduction about Eurotube. Thank you.
Mm-hmm. Thanks, Natalie. Maybe by then we would have already our test track, so perhaps Swissloop or other student teams would be able to test it. Mainly, my name is Lamella Liner. I'm already since 1 year at the Eurotube Foundation, working as a full-time employee, vacuum mechanical engineer. Just a short wrap up about what Eurotube is about. So mainly, we are a foundation categorized as research institute for national importance. Via this status, we have been granted with from the state with a grant with which we make use to develop our technologies. So as you can see on the right-hand side, we not only concentrate on the research and development of our infrastructure, which is our main focus, but also we enable an incubator and transfer platform where other teams and academia and industry can get together to joint develop technology towards the Hyperloop industry. And last but not least, we're also heavily involved in certification and regulation efforts on a European level, where we try to standardize and to set the Hyperloop technology in a common path, such that it can be used in Europe as a first step, and then worldwide in a second step. Mainly looking at our mission and roadmaps, we are targeting now in 2023 our first prototype, so-called demo tube, which is a 120-meter low-speed demonstrator located in Dübendorf, where we also have our laboratory. Here, this test track will enable us to validate our technologies, not only on the side of the infrastructure, but also on the propulsion side, for the so-called Alpha tube, which is then the full-scale tracks high-speed test track located in Valle. Here we're talking about a test track where velocities up to 900 kilometers per hour can be achieved. As a parallel effort, we're also developing models within the so-called TuneTube mission, where feasibility studies to potential commercial routes are being studied, and evaluating where it makes sense to build routes to connect cities and then continents further on. To give an overview about the technologies and research projects which we have been carrying out throughout the last years, you can see on the top left the first prototype of our concrete shell, so-called Alpha shell, co-developed with Creabeton. In a second iteration, as you can see on the bottom right, we permeated the concrete tube with a polypropylene liner, which we successfully tested under vacuum to reach the 1 millibar, which is the pressure which we are aiming for our test facilities. And also a picture of how different types of liner have been tested can be seen on the left-hand side. And on the bottom right, you also can see a prototype of a valve, which we are co-developing with the manufacturer Fawate, to have a first prototype installed in our test track in demo tube for next year. Lucas, I give the word to you.
Thank you. So this is us. This is the Institute of Hyperloop Technology. We've also started out as a student team at the University of Applied Sciences and Leer and the University of Oldenburg, and we have then proceeded over to research, actually, from the student team that you can see here on the first slide in Los Angeles. But then we've implemented that into our studies in engineering physics, and now we are focusing on the research side, where we are looking forward to implement a European Hyperloop test facility, a large-scale research infrastructure, actually, at the old Transrapid test facility. And then we're also doing a lot of research and development of special Hyperloop technologies, as we are certain that you probably cannot develop the Hyperloop just by your own. So on the next slide, then you will see the large-scale test infrastructure. Just to give you a little bit of a gist of how big this test infrastructure actually is, where the Transrapid has been developed. At the bottom right, you can see that it's 16 kilometers from the bottom to the top. It's probably actually a little bit longer because the 60 kilometers is just from the two switches. And then the bottom circle is 2 kilometers in diameter, and the top circle is 4 kilometers in diameter. And if you would, and here in the picture, you can see the top circle actually. The whole test infrastructure has a length of 31 kilometers and a footprint of 12 square kilometers, 13 square kilometers. So it's actually quite a large area that you would need, and you could just reuse this test facility here, offer services to researchers and to the private sector, and get everybody to work together on this shared vision of Hyperloop. On the next slide, you can then see that we have phases mapped out for this. So there's 3 phases which you would need to start this. So at first you would look into the superstructure, because as most of you probably know, there is still a lot of development on Hyperloop going on, and not everybody agrees on the special subsystems. And there might actually be a lot of development and innovation going on in the subsystems right now. So that's why you start with the superstructure, start with the tube, set up a few of those, and test how elongations and weather and everything like that is affecting the infrastructure. Actually, funny to say that the second picture, in the second picture, you see the Transrapid running, and it was actually only performing from 10 o'clock in the morning to sometime in the evening for some days, because the temperature variations were too high and the track was bending a lot due to these temperature changes. So there's a lot of things you can actually start with early on, and at the end you will have to do the 32 kilometers infinite loop, where you can just test full scale, test all year round, and basically all around the clock. On the last slide that I've brought you today, you can see a few of our projects. So I've already told you about the European Hyperloop Technology Center. On the right side, you're seeing a European Union map. That's because you, of course, need a lot of countries to engage in that, and you can't just do it by your own. So you can see a lot of partners that we've already acquired for that project. We are also working on one of the points that we are looking into is transportation, and how does Hyperloop fit into transportation. So that's what we are doing in the Epicenter project, which is an EU project where impact of new technologies and trade routes is studied. So that's where we are doing a lot of logistics related Hyperloop research. And then there's also the Hyperloop development program, where we are looking into the European Hyperloop roadmap and into large scale research infrastructures. And with that, I would like to conclude our slides and hop over and give Elias the word.
Hello, everyone. My name is Elias. I'm team leader of Team Hyperloop, and I'm happy to represent our team today. Yeah, again, I'm pretty excited that we can have the Vacuum Transport seminar on time, another session, since we benefit a lot from it, not only presenting our own subjects, but also getting inspired from the other topics. That's pretty cool. Let's start with our history. So we also took part in the SpaceX Hyperloop pod competitions with quite a big success. Our fastest pod was 482 kilometers an hour, which is pretty good. The team developed over time, as you can see in the pictures below. We increased in size. Right now we are around 90 team members. And the team spirit that can also be seen from the pictures is still driving in us and is motivating us to work on our current project. Yes, that current project would be, well, it started with a small scale ring that you can see here. It was seen in our first slide on the right-hand side. That's in the past. Now we're really working towards this full-scale demonstrator. This is where all the energy basically goes into. And then we have more steps, more major steps towards this Hyperloop technology in a transport environment. Why we, back to the slide, yeah. Why I think we can achieve this big mission is because we are positioned in quite a unique setting. We have the Bavarian government supporting us, not only at the press events that we're holding, but also in this whole Hyperloop vision that they're creating for, within Bavaria. Then we have TUM, so we have quite a good contact to all the professors in different environments, and also we have a lot of TUM students who benefit from that, with a big background in technology. And last but not least, we have all the industry partners that were along the road during the competitions who are going to support us also during this project. Yeah. And the research areas we're following are, as I said, the technology development of the demonstrator, then some simulations and modeling, feasibility studies and route planning, as well as safety analysis. And we also have some talks coming up from our side, so happy to announce them in the later sessions. Thank you very much.
Yeah, thank you. I'm Pia and I'm representing Zero Hyperloop here today. We're really happy that we can also be a part of the vacuum transport seminars. We are quite a young team. We were only founded in May 2020, so we are only in our second season, and we right now have 71 motivated team members from actually 4 different universities in Baden-Württemberg. And they have all quite different fields of study, so we have a quite independent team, and it's really great to work together with them. And right now we are focusing on building prototypes for the EHW. In the first season, we built our first prototype with a linear induction motor, as like you can see on the next slide. We took part with it in the EHW, and it was great to see it run and perform and reach up to 74 kilometers per hour. And yeah, did the slides change for you guys? No, okay, thank you. And yeah, the acceleration we achieved was like 5.4 meters per second. So yeah, we were really happy to achieve this in such a short time. And now for the second season, we want to build on that what we already achieved. And we're going to build we are building 2 prototypes this year. One as like the pod, like a second iteration of it, where we're going to focus more on the shell, the battery, and also our frame. And then we're also going to go more into like a research or project for us and look a bit more into electromagnetic suspension and do another prototype with this concept as well, that we're doing more research now with theses on like general Hyperloop topics, and one of them is also going to be represented here later on in the series. So yeah, thank you very much for having us here as well.
Thank you very much to everyone for presenting your organization, and yes, welcome also very much to the audience. Just a quick overview, what is the goal of the whole seminar? So, I mean, as you saw, there are many different organizations participating. So the goal is really to create a platform where all of us discuss and present what we're working on, like to update also the other organizations, kind of to give information what everyone is working on, and also to provide a platform for discussions between us, but also with the audience. So this is mostly the goal of the whole seminar. As you can see, so it's every Monday from now on, from 6 to 7 Central European time, and the whole schedule you will find online. We have a common website altogether. It's vacuumtransport.org. On this website, you'll find the schedule of this semester and also all the previous editions. The whole seminar is recorded, so you will find all the recordings also on the website. Then the next quick information, we use this tool called slido.com. It's online, so you can either use it via your web browser or with your smartphone. You can go to slido.com and enter event code, which is always the same. It's always Back Transport Seminar. And there you can put your questions either with your name or also as anonymous. And exactly, so during the session, you can post all your questions there, and then after every presentation, we will go through the question moderate during our. Then we also offer the possibilities for thesis. So this is now between Swissloop and Eurotube, but we can also quickly switch to the other organizers, to the partners, exactly what their offers are of thesis. And if you're interested to do a thesis with one of our organizations, don't hesitate to reach out to the corresponding person. And there's always really a lot to work on, a lot of interesting studies and research work. So feel free to just contact us, reach out to us, and we're sure we're going to find a lot of interesting opportunities. So this was it from the introduction side. Again, thank you very much for everyone who attended to this introduction part. And now we will switch over to Swissloop Tunneling. And they participated in the Not a Boring competition of Elon Musk last summer. And I will quickly hand over to Daniel, and he will give a short introduction of Swissloop Tunneling and their talk today. Thank you very much.
Great. It's exactly as Natalie said, we have today the pleasure to receive the first Hyperloop team involved in the tunneling industry, which is going to present a bit more in detail about their first tunneling machine, which competed in the Not a Boring competition of Elon Musk, achieving to reach a second place worldwide in the competition, and also getting to know a bit more into their liner technology, which enables the fast construction of the tunnels. So Luca Tremondi is head of mechanical and civil engineering at Swissloop Tunneling. He's also co-founder of the so-called European Tunneling Week, which is the competition which will take place from now on in Europe regarding the tunneling boring machines. He has a wide expertise in mechanical engineering, the background, and then also expertise in tooling and machining. So very happy to welcome you, Luca, and exactly looking forward to hear more about the presentation. Lucas Hella, he's also head in mechanical and civil engineering at Swissloop Tunneling. He has a broad background already in the civil industry with internships in very prominent companies, and together with Luca, they co-developed, co-led the mechanical and civil department of tunneling. So without any further dilation, I would like to give the floor to you guys, and very much looking forward to the presentation.
Thank you very much. Thank you for the introduction to our persons. We have prepared a slide for introducing ourselves, so I think we can neglect that now. Generally, we have prepared a slide deck for introducing the project at the beginning, introducing Swissloop Tunneling, talking about the project, talking about this competition that Daniel mentioned, and also talking about our tunnel boring machine that we've built last year and are continuing to improve. That will be the first part of this presentation. And then we'll go over to the second part, which consists of the continuous tunnel lining technology, where we give an introduction to general status quo in tunneling, what is the issue currently, and then introduce our 3 engineering solutions and how we think they can be a big benefit to this industry. To us, quick introduction. My name is Luca Ontrum. I'm head of mechanical and civil engineering at the project. I've been in the project for 1.5 years approximately. And then maybe Lucas.
Yeah, I am the head of infrastructure and logistics. We recently just updated this, so Daniel, you're maybe introduced it wrong, but it's fine. I was head of mechanical and civil engineering. I handed it over to Luca for now, and I'm taking over infrastructure and logistics, but helping out anywhere I can, because I've led many subsystems on the way here. I started this journey with lead of soil erosion, which is the cutting head and the transportation of the material from the cutter head to the surface.
Exactly. So then I think we'll go forward with introducing the project. You can see us here, part of the team at the Not a Boring competition in Las Vegas last year in September, which will then be a topic we'll talk about later. Generally, we were founded in 2020 from engineers from Swissloop. So that's the project that you got an introduction for before as well. In 2020, we consist of about 60, now a bit more, students from different specializations, so mechanical, civil, electrical, computer science, and economics. So it's quite a broad spectrum, but we need every aspect of it. And then also the stages are different. So we have bachelor, master, and doctoral students, and also some industry partners that were with us at this competition. The goals of the kind of organization is in the beginning, of course, technical. So we are trying to develop ideas of prototypes of fully autonomous tunnel boring machines. Why that is necessary, Lucas will talk about that in a bit. In that sense, we are trying to advance the speed, and to achieve that, we're aiming to have continuous tunnel lining. And then there are, of course, team goals, because we're a student association. We want to contribute to student knowledge enhancement. So people that might want to get some hands-on experience as a kind of as an aspect as well next to studies can join our team and be part of that, part of the engineering, part of the planning, and so on. And then, of course, we want to drive the innovation in this aspect that we've funded the project in. This is why we are part of different competitions this year as well. Three different very big events, which is the European Tunneling Week that was mentioned once or twice before, and then as well the Not a Boring competition, which you might know a bit about, and then as well an event in Switzerland, the Swiss Tunneling event, which will take place very soon. As a long-term vision, of course, we might want to scale up our machine. You can see it here in this middle picture. It's quite small still. It's of course very helpful to have a small prototype to test out the engineering ideas, but in the long run, we're aiming to scale it up to suit the needs of Hyperloop in this sense. Quickly about the Swiss Tunneling event, it's an event where all our industry partners, of which we had very many last year, about 90 industry partners, they can come, see our machine dig, and also do recruiting with ETH students, which is often very, very interesting for them. And the European Tunneling Week, which will take place in September, where multiple European teams that took place in the Not a Boring competition kind of founded this organization. And the topic will be quite similar. We're trying to dig a miniature tunnel, and we compete with other European teams. It will take place in England, but very soon. So in the next iterations of this event, it will take place in Switzerland and Germany as well, because the founding members are from there. Then this very well-known 2021 Not a Boring competition took place in September last year. We had the boundary conditions to dig a 30-meter tunnel with a diameter of 0.5 meter, and we could encounter many different types of sand, types of gravel, types of limestone, which is why, for instance, in this picture you see the borehead. We didn't have one specific task to dig one specific type of soil, but there were multiple things that we had to be prepared for. And also it's not easy to get boring probes from overseas, which made the whole thing a bit uncertain in the beginning. The goals there were, as well as it will be in the future iterations of this competition as well, to maximize the speed, to fully automate the machine, be as precise and safe as possible. Participants of last year were the well-known MIT, TU Munich, then from Mosbach in Germany, there was a team, and also from Warwick, England. This is just 4 well-known names of these 12 participants that got to the final of this competition. And yeah, the event took place in Las Vegas, as mentioned before. We finished the last project year by winning the Innovation Award in the 2nd place at the competition. And this gave us a very large reach in Switzerland and also internationally. We became the largest Swiss student engineering project, and we were covered in over 70 media articles Some of them you can see here, 20 minutes, Südostschweiz, SAF, and so on. And we approximate that about 1 million Swiss people were reached. Exactly. Now we will cover a bit of aspects of the tunnel boring machine. So now it will be technical. Our TBM that we built last year is called Groundhog Alpha. The length is about 7 meters. It's about 2.5 tons heavy, and can propulse forward with a force of 200 kilonewtons, which is about 20 tons. And the driving torque in the beginning is 8.5 kilonewton meters. And for us engineers, it's of course very amazing to see that from this concept and beginning, from this rendering, we could manufacture the whole thing, which is in the end very large and heavy as well. Exactly.
All right, we'll go into a bit more detail now with the continuous tunnel lining. I think it's more interesting to know about how we construct it and why it's important to construct it continuous. So Luca mentioned this already. I wanted to give you a short overview of the problem that we're having or that we're facing in the tunnel industry. So what we compare ourselves to, because it's a small machine of a diameter of 50, 60 centimeters, we're competing against press or pipe jacking. So pipe jacking approach is just pressing in prefabricated segments, mostly concrete with steel tubes inside. And that will be pressed from a start to a finish shaft. You need start and finish shaft. I get to that. And you can do it like a dry or liquid conveying. So that's how you get the material out from the front all the way to the back. It can be done continuous. That's not the issue there. Disadvantages are with this approach that you have to press from the beginning all the way to the end. And the propulsion force is then proportional to the length, because friction along the length increases obviously the further you get, and this requires large pressing plans. It needs anchoring and conditional construction shafts, as you can see in the picture on the right. And this pressing of prefabricated lining also means that you have sequential operation. This comes with time losses, and oftentimes the supply is decisive. So you need to lift in those segments, you need to weld them together, or yeah, it's just a huge time loss that we need to get rid of. And it's mostly tied to a straight line. You can imagine if you push straight and then you need to do a curve, the propulsion force increases substantially. Also, if we're talking about vacuum transport today, I think it's very important to know that our lining is more airtight, I guess, than any other prefabricated lining which has segments. So you need to seal off the gaps. And also, if we're talking about controlling the machine, oftentimes those workers on site are not or knowledgeable workers on site are very expensive. So open loop control is required in those kind of machineries. We want to close this loop, so the machine decides itself what to do. That takes away the knowledge part of a worker's capabilities, and I think it's much more safe and much more for this time, I guess, much more better approach. So I guess continuous tunnel lining in general, you need to know that first off, erosion and transportation of the material needs to be continuous. Then the lining production needs to be continuous. Propulsion, so actually advancing forward, needs to be continuous. And also the supply, which is mandatory or even decisive in most cases. So this is the approach, which is continuous tunnel lining production and so forth. This is very, very good or easy for a closed loop control. So Swissloop Tunneling's solution, we're pursuing this in terms of actually looking for a solution for continuous extrusion of polymer as a lining, not concrete. It's not specifically, it doesn't need to be concrete or polymer. It's something we're looking into, but it needs to be fast curing because we are clamping against it and propulsing yourself within the tube that we're producing. We're pressurizing it sort of. And that requires, if you know from statics, you need tensile strength to activate this propulsion or clamping force. And then it also needs this bracing possibility in loose soil, which means that, I mean, gripper machines are, this gripping machine is done in many large TBMs, but it's never done in soft TBMs, in soft soil. So this is a huge approach or a huge advancement from our side. And I think we're pursuing now 3 approaches. You can see on the right. So we have the Lamella Liner, which I go into quickly now, and then the mold liner, which is a pressurized system. The other one is a flow controlled system, and then an extrusion one, which is using another type of polymer, one component polymer, and that will be Lucas' part then. So for Lamella Liner, that's what we're currently looking into. As you can see on the bottom, it's actually being built. It's a prototype still, but it's built. It consists of 12 nozzles, which 3D print this tunnel lining segment. We have an outer and an inner lamella, which is a sort of a sandwich then. The outer lamella is a glass fiber lamella, and the polymer filling is a 2-component MMA. It's mixed shortly before, so you can see those segments here with static mixers inside of them. So they mix those 2 components and they are being activated, and then it will be extruded and filled within those 2 lamellas. The inner lamella is just for cleanliness and like a safety film, I guess. We need about 14 millimeters. I'll get to that, how we're gonna, like how we determine 14 millimeters to resist gripping forces and propulsion forces. And it's obviously, as I said, a continuous process, because 3D printing in general is a process that is continuous. So the huge problem for us was that the Young's modulus or E modulus was very low with polymer in general. So polymer, as you know, is very soft compared to concrete or steel even. So the modulus is around 5 gigapascal for the polymer that we're using, maybe sometimes lower for lower hardening times. And then we have a soil that we just took for like a friction angle of 25 degrees and a weight of 18 kilonewtons per square per cubic meters. And then we assumed or looked into gaps between soiler and liner, because you need to imagine that the soil is actually the support for this liner prefabric or this in situ created liner, which is then pressurized not only in radial direction, but also in longitudinal direction with about 20 tons of thrust. So it needs to withstand that, and we did some buckling calculations and simulations for that. And you can see the clamping forces are being calculated with a friction coefficient of 0.5. We have individual clamping of around 51 kilonewtons, and the total, as I said, about 20 tons. And also, in addition to all of this, we have a curvature that we want to do of radius 167. That's just how it is with the competition that we're participating. And this leads to a huge buckling problem. And results of that calculations were that we need 14 millimeters for the stiffness. So if the Young's modulus or the E modulus is low, you obviously need a huge stiffness. So the I, if you guys are familiar with this. And so local buckling was a bigger problem than global buckling. We saw that during clamping onto the liner, the individual sections of 51 kilonewtons, the local where you clamp and go onto the liner, that stiffness there is very low because the hardening time is the lowest for that. And we need a lot of experimental tests to verify those results, because they're very, very theoretical and based on very much assumptions that we haven't or experimental proved yet.
Exactly. Thank you so much, Lucas, for this presentation part. I will talk about these two other systems that just this year we started taking a look at. They're still in designing phase, and some of the aspects are in the prototyping phase. But I think it's still valuable to know in which direction we would like to move to simplify the system. As you might have seen earlier, these mechanical aspects of these liner systems are still very interdependent and not very simplified. So we are thinking of two new systems. One of them is the tunnel extrusion system, where we're making use of a heated screw that we use to liquefy different types of polymer and then extrude out as a tunnel wall. And with this, we can use a broad spectrum of materials, broad spectrum of polymers, cut down costs. We can use perhaps even recycled plastic. We could add additives like glass fiber snippets to increase the strength and so on. That is something we're currently taking a look at, but again, it's only in the designing phase. And in the beginning, we're doing a 1 to 5 prototype just to check our assumptions. Then this next system is a bit closer to home, to what we already have standing in the workshop downstairs. It's the mold liner, which is until there's the dosing aspect or the mixing aspects of the two components of the polymer will stay the same from the input of the polymer, but then the output changes. In this case, we are not using lamellas anymore, or rolls to unroll these lamellas, but this time using also an injection kind of way to inject this hardening polymer out. Again, this is also in a designing and testing phase to check whether the materials that we would like to choose as layers in between work with our polymer and so on. Advantage with this would have obviously be that the mechanism is much more simplified, which is always great in engineering, of course, but then as well that we can keep the pumps and the setup for the dosing, the setup for the mixing, which is a huge part as well. Yeah, this is it for kind of an overview of these new systems that we're taking a look at, and we thank you very much for the interest in this topic and pay attention to the presentation. And I think now it's planned to have a bunch of questions as well.
Thank you very much, Lucas and Luca, for your presentation and your insight into Swissloop tunneling, and also all the technical specifications. That was very interesting. Exactly, we would like to head over to the questions now.
Should I stop the share for this?
As you want. Yes, you can. Yes, you can stop. Okay, so the first question we received, somebody's wondering, what is the biggest challenge which is preventing you to scale up the system to a bigger diameter?
Money. I think for most of us, it's going to be the same thing, because we're a foundation or a student association, and I think for us, it's money which buys us infrastructure to build up something bigger. Because as you've seen, it's already 2.5 tons. I don't know how much the pod weighs, that your Hyperloop pods. I think 200 kilos.
200 to 300 kilograms. Yes.
Yeah, so it's about 10 times this. So it's very heavy and to move around things. And if you scale up this diameter by 20 centimeters, even, you double the area that you want to dig through, because obviously the radius squared. So it gets very heavy. It gets very tight or heavy on infrastructure. So that's a main issue, I guess, for us to scale up. And also, I think I want to add on this. It's not really necessary for proof of concept to scale this up. As we've seen now, the interest is here for us to build something that is even commercially available for people to test it out. We're in talks with Tiefbau and Zurich that want to test this out and see some tunnel created by our machine, which is very exciting for us. And yeah, I think it's a great diameter and a great compromise between a proof of concept and scaling up for Hyperloop.
Okay, that's very good to know, because I just wanted to jump in with a follow-up question. If you see a comparison, or if you would predict a comparison, but I guess then it's even better that you can already test everything necessary with this size. Then the next question is, how do you ensure that the boring hole does not collapse, is linear enough to guarantee the hole stability?
It's linear.
Sorry, it's a
Liner, I think
line.
the liner.
It's a liner enough and guarantee the stability.
Yes, very good question. I think it's great to know that the decisive factor here is actually not the earth forces that are acting on the outside onto the liner, but actually the propulsion force or the clamping forces that were pushing against it, and also on the longitudinal direction. That is the decisive factor. So it's not collapsing in any way. So we can go quite deep with even water coming in, or it's even watertight, and that's not an issue.
All right. Then there's one question which is with regard to the first one, and is now more regarding a scientific point. What is the biggest challenge for scaling the machine up from the scientific point?
Okay, you want to, or should I?
Maybe, yeah. So we've now different subsystems. So we have 3 different subsystems. For one of them, it works very much with heat. So this extrusion system, it's very heat dependent. And so I think from a scientific standpoint, scaling this up will be a large issue, because with our diameter, at the moment, we already need 30 to 40 kilowatts to heat it up. Even then, the question is how to cool it down again. So scaling this up is an issue with heat. For the liner mechanism, as is currently in the workshop. So as Lucas described it, I believe it's going to be difficult for the polymer to be kind of ejected by the nozzle, and the liner being kind of rolled out from the surface. And I'm not sure, we've gotten feedback, for instance, that this technology when scaling up is probably not even kind of the best way. Kind of this polymer solutions, they're currently in use for smaller tunnels, so for water pipes, for instance, for oil pipes, for cable pipes. So when scaling up and using it for transport ways, then I think we might need to take a look at extruding concrete. For this specific material, there's of course this cost standpoint. We already need a lot of cost per meter with the raw polymer as we have it. It's 2-component MMA kind of adhesive, but that's not scientific. The cost is not a scientific factor. So I'm not very sure. If Lucas, you have another input on that.
Yes, so I want to quickly add on this, because I think scaling up with the current design is, as Luca described it, not feasible. But what we are looking into is scaling up with prefabricated elements that we transport in and doing the same thing. So same idea with propulsing in the newly created liner system, but then using prefabricated elements and just welding them together. This can be done by polymer welding, or by just purely welding the 2 materials from the prefabricated material together. And I think that's a very interesting way to sort of skip this problem that we're currently having with just very expensive material and having it created in situ, having the heat created in situ. And I think that's a very good solution for scaling up if we are going to do that.
In the beginning of this new season, we've already also thought about very new solutions. So how can we not tie ourselves to the current system and think about very new things? And there was the idea that came up for using steel, kind of transporting in steel parts and kind of welding them together, which is something that for larger diameters we might be able to take a look at again. However, for the current diameter, it's very limiting in transporting segments because they don't fit. And yeah.
That's a very good question.
Yes, and thank you very much for the very detailed answer. The next question, which parts of the boring machine would need to be replaced earliest apart from the frontmost boring part and the boring teeth?
So earliest in the sense that
I
it's
guess
going
in
to be used
terms
up
of,
or destroyed.
I assume
Yeah.
it's in regard to of use.
So I believe for sure it's going to be part of the erosion, because that's the one that gets the most mechanical stress, particularly the rollers. So at the moment, the rollers, they're, as I mentioned in the beginning, they're designed to be able to encounter many different types of soil, which is why they have this special geometry, so that if there's hard stones coming or if there's soil coming, it's making use of this geometry the very best way. So you might have seen this teeth in the rollers, which is not something one conventionally does. But then if there's that's something we discussed as well with the company that produced it. If we encounter a wall of concrete or a wall of a large stone or something, then these teeth that are part of the rollers might hurt us very much, because if they're blocked by this wall that we encounter, then they will be eroded very quickly, and that's then probably the first part to go.
All right.
Lucas, do you have additions to it?
No, you can go ahead.
All right. Then I think it's also an interesting question. The next one: will the liner be airtight, or will there be a need for airtight pipe inside the tunnel you created for Hyperloops?
So I think for the end result, it needs a bit of after work, going through the tunnel and checking everything before actually letting it run with your vacuum machines. But I think it's very much because it's an extruded and also over a centimeter thick polymer. It's going to be airtight, but I think it needs some after work, as it usually does in tunnel construction, that you need to go through and check everything and see if it has leaks and stuff. But
I mean, that's what's being used for current polymer tunnels as well. When there's a leak, when there's a kind of a destroyed part, then there's these robots that they can go inside and inject this glue to the kind of parts where there's leaks or holes. So that's currently being used for infrastructure pipes to fix them after actually digging them to the ground, so that they don't completely have to be removed. So that's something that we could use to make it more tight.
All right. Yes, I think sounds like a lot of good ideas. Then the last question we have, how would you want to provide the power to the boring machine? How much would it be for a 3 to 4 meter diameter?
well, from experience, I know that it is going to be a lot. So what we're currently using on our machine with the tunnel extrusion stuff that we're doing, and also the motors that we're using, and the supply chain that we're having, so all in all, it's 100 kilowatts for this diameter. But as I said, it's going to be squared if you're going upwards, because the boring head gets proportionally larger. And from what we've learned, we were on excursions for many large TBMs, 3 to 4 meters even, and I think there it was correct me if I'm wrong, Luca, but I think it was something around 950 what they were currently using kilowatts. That answers the question.
So maybe the first part of the question was, how do you provide that, right?
Yes.
So at the moment, we're just using cables to the inside of the tunnel, which obviously needs very long cables, it's 40 meters. That's the way we provide the power for all the systems inside. But much of our machinery is also on the outside. So to transport the polymer in the liquid state into the machine, we need these very large pumps. they're situated in the outside. So there it's very clear how to provide it.
Okay, so thank you very much for the question round. The time is up for this week's seminar, and also we're done with all the questions. So again, thank you very much to Luco and Lucas from Swissloop Tunneling for joining in today and presenting your work. It was very interesting. Thank you very much for your insights.
Thank you.
Thank you. Thank you for having us.
Thank you very much. And in that sense, also, thank you very much to the organizations of the whole seminar. So to Daniel, to Pia, to Elias, and to Lucas. And we thank also the audience for tuning in today, and we're looking forward to welcoming you again in a week for the next seminar session. Again, as I said, all the information you find on vacuumtransport.org. And until then, we wish you a good week and see you in a week. Thank you very much, and goodbye, everyone.
Have a good evening. Bye-bye.
Good evening.
Thank you.
Bye-bye.
Bye-bye.